Today is April 6th, and this is our graphing square root functions video number 2. Most days I will try to make it into one video, but it does cut off at 15 minutes. So today I'm going to have to flop into a second video, but I'll try to wrap up here pretty quickly. We left off with this graph on our last video. When a is not equal to 1, I know that my function is going to behave a little bit differently. And because I'm taking the square root of the number, it doesn't always do exactly what you think it's going to do, other than that multiplying times 2 makes it change faster. So on those, I always want to make a table. On this one, I actually went over 1 up 2, over 4 up 4, and that pattern gets a little confusing, so on these I would always make a table. So the next thing that we want to be able to do is to write an equation from a graph. So say I give you this graph to start with. The first thing that you're going to want to do to write the equation is to find the quote vertex. So I'm finding the point where it starts, and I know that this is at 3, 2. So I'm going to take that number and I'm going to plug it into the equation. And again, my basic form of the equation looks a lot like vertex form for a quadratic equation, where h and k is that beginning point. In a quadratic equation, it's called the vertex, and that a in front of the square root symbol makes the function behave in a little bit more. It multiplies everything times a factor. So I basically am going to start with this vertex form. I'm going to plug in my, again, it's not really called a vertex, but I'm going to plug in that beginning point, so that's 3, 2. And then I'm going to look at my graph to see if a is something other than 1. So I'm going to start at this point. As x changed by 1, y changed by 1. As actually I'm going to say as y changed by 1, x changed by 1. As I went up 2, I went over 4. As I went up 3, I went over 9. So because that pattern follows my typical squaring pattern, I know that a equals 1. If I examined this a, or this beginning point, and I noticed that it wasn't following that typical pattern, then I would know that a was not equal to 1, and I would have to do a little bit more work to find what a is. I'm not going to ask you to do that. It's a little bit more complicated than what we need to do. But if I had kind of the typical function where a equals 1, I should be able to write it using just that vertex point. I also should check a couple of points. So as I look at my graph, I know that my next point is 4, 3, and then I've got a point at 7, 4. So I'm going to plug 4 in for x and make sure that it equals y equals 3, and in this case it does. And then I'm going to plug 7 in for x and make sure that it ends up being 4, and that does as well. So that's a quick overview of how you can write an equation from that graph. I want to come back to this idea of the domain being restricted, because the number under the radical symbol, the radicand, always has to be positive. So if you're asked to determine the domain, one way of doing it is to graph the function and then to just look and see that all of your x values are always greater than a certain number. But keep in mind that what's driving that is the fact that the domain is restricted to the values that make the radicand greater than or equal to 0. So say, for example, in our parent function, my radicand, if x is the radicand, then the biggest number that x can be is 0. So my domain is going to be x is greater than or equal to 0. If I have x plus 2 under the radical symbol, I know that it has to be 0 or greater than 0. So x could be -2, it could be -1, it could be 10, but it could never be less than -2. So in that case, my domain is restricted. X has to be greater than or equal to -2. So I figure out what the domain is by asking myself, what is x if x plus 2 equals 0? On this one, I want to know x minus 5 equals 0. What would x have to be if this number was 0? So in this case, x would have to be 5. So that restricts my domain so that x is greater than or equal to 5. You'll have some problems asking you to do that on your homework tonight, so you can come back to this section of the video if you need some help with that piece. And then finally, I just want to summarize. We've talked about all of the pieces of this, but I just want to summarize the parent function and then the translations that might happen. So again, this is the parent function of a square root function. Another way that I can write it is y equals x to the 1/2 power. If I have the parent function and I add 3, and the plus 3 is not part of my radicand, then that's translating my whole graph up 3 units. If this were minus 3, it would be translating it down 3 units. Again, at this point, we should be so used to that pattern in other types of functions that that should be pretty clear to us. Again, another way to write this is y equals x to the 1/2 plus 3. And I'm hoping that you're seeing the similarities with quadratic functions written in vertex form, because that will really help you remember a lot of this. Our next one is if I have something under the radical symbol, that actually shifts my, translates my function right and left. So if I have -1, it's going to translate my whole graph right 1 unit. And then this plus 3 again is going to translate it up 3 units. Again, if I write this in the form with a rational exponent, now it's really looking like vertex form, with this being the h, this being the h, and this being the k. And then finally, my last translation is if I have a negative symbol in front of the square root symbol, that's going to reflect my graph across x equals 0. So in this case, across the x-axis. Then there really is one more. If I have y equals 2 to the square root of x, I know that that 2 is going to exaggerate everything. And I'm not going to try to state the exactly what happens here because it's a little confusing to say and it's a little confusing to understand. But I would say that this makes my function a little bit, it goes up faster. The y value changes faster because everything's being multiplied times 2. So I just want to be really careful if I have an a that's not equal to 1, that I'm looking at that, making sure that I'm making a table so that I know exactly where those values are. All right, that's it for graphing square root functions. For practice tonight, you just have 7 problems. There is a link on the Google slide. And again, if you, as you're doing those problems, keep thinking back to vertex form on quadratic functions. It will not only help you understand square root functions, but it will also give you a deeper understanding of the vertex form of quadratic functions. All right, see you tomorrow.